Hey everybody, welcome back to Boot Camp here for our nephrology section. We are going to talk about something very, very important today and extremely commonly tested, which is acid-base physiology. I would argue this might be one of the more high-yield things for you to know, the entire physiology section. So if you all are ready, then off we go. So first, let's start with some fundamental principles and talk about what acidosis and alkalosis mean. Acidosis is an increase in proton levels, and alkalosis is thus a decrease in proton levels. It's very important that we don't confuse these terms with something that's very similar but different, and that is acidemia or alkalemia. So acidemia is the overall state of the pH in the body. So if we say somebody has a blood pH of 7.3, we're saying that they have acidemia. This is similar but notably different from saying that somebody has acidosis or alkalosis going on. Acidosis or alkalosis is referring to a process in which we're getting a change in bicarb or proton levels. So it's important to note that somebody could have a simultaneous metabolic alkalosis and respiratory acidosis. So you can have both of these problems at the same time, and then we have to figure out what's their overall body pH, and that will determine whether or not they have an alkalemia or an acidemia. So for example, when we say that the arterial pH is approximately 7.35 to 7.45. Above 7.45 would be alkalemia, and below 7.35 would be acidemia. It's also important to know that these are approximate ranges, and depending on the resource that you look at, these values might differ slightly. But in general, this is a pretty commonly used range for a normal blood pH. There's a couple more normal values that I want you all to know, and that is a normal bicarb of approximately 24 milliequivalents per liter and a normal PCO2 of approximately 40 millimeters of mercury. Again, there are a range of numbers that we consider normal, but for the sake of what we need to know at this level in terms of our calculations and stuff, we really just need to know kind of what's an approximation so that we can use that and simplify the things that we need to know going forward. We don't have to make things more complicated than they need to be, so let's not. It's also important to know that the acid-base physiology in our body is regulated by two primary organs, including the kidneys, which are responsible for bicarb production and hydrogen excretion, and the lungs, which primarily help with CO2 excretion. Notice I said that this is a tightly regulated process, and that should make sense to you because our pH and our acid-base physiology is actually super important for that term we love to talk about, which is homeostasis. So next we're going to talk about some important formulas that you all need to know for figuring out these acid-base physiology problems. This is often a very confusing part for students because they don't have a system, they don't have a process, and that's my goal with this video today, is to give you a system and a process. And if you apply this every time, honestly, these questions can become easy. These can become simple points for you on test day if you just have a system in line. So here we go. So first we're going to talk about the Henderson-Hasselbalch equation, but before we do, I want to take one step back and say, what is the equation for pH? And if you recall, it's this right here. It's that pH equals the negative log of the hydrogen proton. So this tells us two things. One, that pH is measured on a log scale. So every one change in the log scale is actually equivalent to a 10-fold change. And second, it shows us this inverse relationship between pH and hydrogen protons. So if hydrogen protons increase, pH is ultimately going to decrease. And vice versa is also true. If hydrogen protons decrease, pH would increase, and we have an alkalotic state or an alkalemia. So getting back to the Henderson-Hasselbalch equation, you can notice that if we have pH and PCO2, we can calculate our bicarb, or other things can happen, right? If you have two of the variables, you can essentially calculate the third one. And this equation is also important because it tells us about the organs that regulate our pH, right? We said that our PCO2 is going to be regulated by our lungs, and our bicarb is going to be regulated by our kidneys. I would say it's very unlikely that you have to have this equation memorized where they ask you to actually input information for it, but it's important to understand it conceptually and how the variables can change. So the next equation we're going to talk about is Winter's formula. So Winter's formula is listed right here. It's PCO2 equals 1.5 times the bicarb plus 8 plus or minus 2. And this is actually going to make a lot more sense when we start doing practice problems, but essentially Winter's formula is something that we use in a state of metabolic acidosis to determine if there is an appropriate compensation being made. So what do I mean by that? When we have a problem, such as metabolic acidosis, that is saying that our proton levels have become elevated. Our body is then going to respond in order to return to homeostasis by doing something else to balance it out. One of the ways it can do that is by altering our respiratory rate, which can impact our CO2 and thus kind of modify essentially what our proton levels are. So by having a metabolic change in terms of protons or bicarb from the kidney, our lungs can then work to try and balance that out. And when we're calculating Winter's formula, we're asking the question, are the lungs responding appropriately? As in, given a metabolic acidosis is present, are the lungs responding appropriately? Do we have the expected amount of carbon dioxide in the lungs? Is it too high or is it too low? We can calculate that with Winter's formula. If Winter's formula indicates that the CO2 level is outside of the range we would expect it to be, that indicates we have two disorders going on in which multiple metabolic cause and a respiratory cause. And we will talk more about this in the next video when we do some practice problems. I promise it will make a lot more sense at that time. And the final equation that you will need to know is that of the anion gap, which equals sodium minus bicarb minus chloride. And you might be saying, David, what is the anion gap? And that's a great question. So let's talk about it. So essentially, the anion gap is looking at the difference in unmeasured cations versus unmeasured anions. So remember that everything in the body is homeostasis and electrochemical neutrality. So in general, our positive charges, indicated over here by our sodium, should be balanced approximately by our negative charges, indicated by our chloride and our bicarb. The anion gap, the gap refers to the unmeasured negatively charged anions in the body. So some examples include proteins, sulfate, and phosphate. However, there are various physiologic reasons or even pathologic reasons that this anion gap can actually change, in which we get an elevated level of unmeasured anions and thus a change in the anion gap. And so if a physiologic process happens that alters the anion gap, we have more negative ions relative to the cations that we're looking at. So you can appreciate then that over here we have the normal gap, which is essentially represented by this box right here. But if we have an increased anion gap, we have an increased amount in this box over here, or negative anions relative to what we would prefer to have or what we would expect to have in a normal physiologic state. Determining this anion gap is very important for patients who have something called metabolic acidosis. If patients have metabolic acidosis, there is a huge list of things that can cause this. In calculating the anion gap and determining whether or not it's a normal or an elevated anion gap is super important for helping you with your differential in terms of breaking up and categorizing which are possible pathophysiologic mechanisms that could have caused the patient's metabolic acidosis. Because it's important to understand what's causing the metabolic acidosis so we can appropriately treat the underlying cause. So now we're going to talk about a stepwise way to calculate these acid-base problems, and we're going to do several practice examples on the next video as well. A lot of times students really overlook this because it seems confusing and it's math and we don't like it, but you're going to continuously get questions on it and you're going to continuously get them wrong until you have a system. I promise you, once you have this system in place and once you understand what's going on, there's very few acid-based questions that they could ask you that will stump you at that point. So if we learn it now, if we take the time and we invest it now, we can get these questions right for the rest of our career. So the first thing I want you to do when starting out with these questions is to set up your formula, which is your pH equals your bicarb over your CO2. And remember, the system matters here so that we're consistent every time when we approach these questions. So the first thing I want you to do is to assess the pH. Is this an acidic state or an alkalotic state? The approximate range of 7.35 to 7.45. So if it's above 7.45, it's alkalotic, and if it's below 7.35, it's acidic. That's the first step. Okay, you're done. Only 4 left. Next, we're going to move on to assessing our bicarb and our CO2. Remember at the beginning of the video, I said to remember the approximate number of 24 for bicarb and 40 for CO2. Yes, absolutely. There is an actual range of normal values, but for the purposes of calculations, we want to simplify, simplify, simplify. And that's what we're doing here. If you remember these approximate numbers, you're going to have a very high success with answering these questions right. So the second thing is to assess bicarb and PCO2. Are they close to normal values or are they off of the normal values? Next, you have to determine what is the primary disorder, as in what is causing the disruption in the pH. Is it a metabolic cause? Is it related to the bicarb? Or is it a respiratory cause, which is more related to the CO2? Then, if we determine that it's a metabolic acidosis, so if the pH is low, we have an acidic state, and the bicarb is low, we can assume that the reason the pH is low is because we are low on bicarb, and thus this is consistent with metabolic acidosis. So the next question is, are the lungs compensating? If we are low on bicarb, we would expect that our lungs would compensate by changing the CO2 levels. Step 4 is to assess the anion gap if it's a metabolic acidosis. I think because there's so many causes of metabolic acidosis, it's the one that's most commonly tested for you all. So be on the lookout for that. And we know that if we determine it's a metabolic acidosis, we can calculate the anion gap using this above equation that we talked about, which is the sodium minus the bicarb minus the chloride. So step 4 is to calculate the anion gap. And then the final step is to assess for compensation. This is where we might use things like Winter's formula, where we might determine, okay, there's a metabolic acidosis, pH is low, and bicarb is low. So what's the CO2 doing? Is the CO2 compensating with the lungs in the way that we would expect it to? And that's what these special formulas come in. So technically, you could be done after 3 steps. You could determine the pH, you could assess the normal bicarb and CO2, and you could determine the primary disorder. However, if it's a metabolic acidosis, there are a couple extra steps to do, which is why I think they ask about it most commonly. This is going to make much more sense in the next video. We're going to go through each of these steps again with numbers and practice problems. So head on over to that video, and I will see you all there to really solidify this information in the step-by-step process.